Hello everybody, you already know what time it is. We're going for more AP review. What the heck? I know I said that there are not that many STEM APs existing in the universe right now, but there still are some, okay? AP Bio and AP Stats is still coming up, so while APs are going on, I am going to be making AP videos. Thankfully for those of you guys who are here for the Olympiad nonsense, that's only gonna last 2 more videos, so don't worry, we're gonna get back to the epic stuff after this. And I completely understand, APs are boring, Olympiads are cool, so yeah. And don't worry, I will reward you for your wait. I have some cool stuff planned, so don't worry about it. But what? Are you saying that Bio is not cool? You know what? Hello everybody, I'm Karar, and today we are going to be doing Unit 1 review of AP Bio. Now of course, AP Bio is on Monday, which is tomorrow, so I'm not going to get any more videos out, so it's only Unit 1. But Unit 1 is probably the one you remember the least. So let's get into it. And also, if I start a series, don't worry, next year I will have AP Bio fully done then. Gonna motivate myself, you know what I'm saying. So let us begin with the chemistry of life. We're going to talk about these 3 bullet points. It looks like very little, but it's actually a ton. Let's do it. Alrighty boys, the first thing we got to talk about are the important properties of water, because water is extremely important. That was the understatement of the year too. Like literally people go to Mars to look for water just because they think that that means life, okay? They got so excited when they saw dried water. No, I don't know what that even means. Fine, no longer running streams, how about that? But anyway, the reason why water is so important is because first off, it makes up 70% of the human body, so it's very important for keeping us alive. And the reason why it's so good at doing that is because it has very important properties. The underlying mechanism that causes all these properties is hydrogen bonding. So let's draw water, right? How does this nonsense work? So let's say this is a water molecule, right? You got your oxygen, you got your 2 hydrogens, very cool. So for reasons that are not relevant to bio, but you could learn it if you went to chem, these hydrogen atoms are not exactly opposite each other, okay? So this angle right here is 109.5 degrees. What does that mean? Well, these bonds are polar, right? So basically, because these bonds are polar, that means that oxygen is hogging all the electrons. Oxygen is going to get a negative charge, and these guys are going to get a positive charge. But because this angle is 109.5, the charges don't cancel out, it's not symmetrical. So now there's a positive charge here and a negative charge here, and what happens when you put 2 magnets together? That's right, they go slam, like that. So basically, what a hydrogen bond is when 2 water molecules come together, and this O is like, hey, what's up, man? I have a negative charge, you have a positive charge, let's hook up. Okay, that's kind of weird. Just kind of. But anyway, so it goes like this. So there's a bond over here, and then another molecule might go over here, and it'll be like, what's up? And these guys go together. So basically, because there are polar bonds between the water molecules and the oxygen become negative, and the hydrogen become positive, clearly, the negative oxygens are going to be attracted to the positive hydrogen. So what the heck is the point of hydrogen bonding? What does it even mean that they hydrogen bond? How is it relevant? Well, basically what it means is that water is attracted to itself. I know that's weird, but it's true. And this property of water is called cohesion. But these waters, because they have positive and negative charge, they're also attracted to other things that have positive and negative charge. Like let's say there's an Na plus here. It's going to be attracted to the oxygen. Positive, negative attraction. So water is also attracted to other stuff. So that's called adhesion. And the way I like to remember it, right? Cohesion is like cooperation. It's the same kind of people working together. Adhesion is when you glue something to another thing. So they're 2 separate things attracted to each other. So in this case, sodium is one thing attracted to water, which is another thing, thus it's adhesion. And you can see this in like a graduated cylinder, right? Like water is attracted to the walls of the container, which is why it creeps up the side. So these 2 basic properties of water, first that it's attracted to itself, and second it's attracted to other things, lead to a lot of cool properties. So the first thing we'll talk about is like hydrophilic and hydrophobic. Now you probably know that philia means you like stuff, so hydrophilic means it likes water, so that means it's attracted to water, and we know that this is possible because of adhesion. So basically anything that has a charge is hydrophilic, anything that's polar. Just think of hydrophilic as can dissolve in water. Hydrophobic, on the other hand, can't dissolve in water, and you probably know a bunch of examples of this, like, you know, oil can't dissolve in water because it's hydrophobic, it's non-polar, and it can't dissolve in water. And this makes sense, right? If something's not charged or not polar, how's it going to attract the water? It doesn't make sense. But the thing is, right, like, a lot of things are polar. Like, not many things are non-polar, so water is called the universal solvent. It's so strongly attracted to everything that it can literally dissociate anything and cause everything to dissolve. Of course, it was hydrophilic. If it's hydrophobic, it doesn't dissolve in water. Okay, one more thing for water, and then we are Gucci. The last thing is, if you've ever tried to boil a pot of water, do not try it. I tried it because I had nothing better to do with my life, and my mom wanted me to make pasta. But basically, it takes forever, okay? It takes like eons to boil water. And the reason for that is because the hydrogen bonds hold the water together, so it takes a lot more energy in order to make it into a gas. And this over here is called the heat of vaporization. And it's high as heck, which basically means that it's hard to boil it. What's even worse is that it takes a ton of energy just to heat it up a little bit, and that's called a specific heat. Now the way I like to remember the difference between heat of vaporization and specific heat is like heat of vaporization is clearly evaporating, so it's energy to cause it to boil. But specific heat is like specifically how much does it take to change 1 degree Celsius. So specific means you're changing it by a specific amount of temperature. So this basically means that it's hard to change its temperature. And that's good for living things, right? Because living things like to have a constant temperature. And then lastly, its density is high. But the cool thing about water is that water is denser than ice. That's because the hydrogen bonds cause it to form a crystal structure once it's frozen. And like the hydrogen bonds keep the molecules separated. But really, you don't really have to know exactly why that happens, but the cool application of this is if you have a lake, right, and you have ice at the top, it's not going to freeze the rest of the lake, because ice is less dense, so it floats on the top. So you guys could be living down here, happily studying AP Bio, and the ice will not freeze on you. Well, I mean, you probably die from hypothermia, but it's okay. Okay, epic, that's all we gotta talk about water. The next thing we gotta talk about is elements and atoms, but I'm gonna very muchly brief over this nonsense because you better know what elements and atoms are, otherwise I'm gonna be extremely triggered at you. Dude, if you've taken any science, you literally gotta know what elements are, okay? Get your act together. No, I'm kidding. But anyways, so elements are all the stuff on the periodic table, right? They're just different types of substances. And each element is defined by its atoms. And atoms are the basic building blocks of elements. So an atom looks like this. It has a nice little nucleus in the middle, cute little nucleus which is positively charged, and it got an electron that's just randomly going swiggling around here. And remember that electrons are not orbiting like a planet around the sun or anything. They're literally like randomly moving around. So don't say they move in a circle, otherwise you're screwed. But anyways, electrons are negatively charged, as I said. But the nucleus, the reason why it's positively charged is because it has protons, which are plus charged, and neutrons, which are neutral, as you might expect. Alright, so the only thing you gotta know about these particles, called subatomic particles, is their charge, right? And you also gotta know that protons are what define an element, right? On the periodic table, the atomic number is the number of protons. And then neutrons make different isotopes. Like carbon-12 has 6 neutrons, but carbon-14 has 8 neutrons. AP Bio is not gonna ask you to do the math, I'm pretty sure, so don't worry about that too much. Also, something you should probably note is that protons and neutrons weigh 1 AMU. However, electrons weigh like basically nothing compared to that, so if you're calculating the mass of an atom, you only had to add up the number of protons plus the number of neutrons. But there is one element that holds a special place in our heart, and that's carbon. Now the reason why carbon has a special place in our heart is because it literally makes up everything. The definition of organic chem is having to do with substances that include carbon. Now what's so epic about carbon? Basically what's epic about it is that it forms 4 bonds, which is, I guess, not that epic, but these bonds, if they bond to another carbon, are super heckin' strong. And because these bonds are so heckin' strong, biology likes to use it as a backbone. So you'll often hear the thing carbon backbone. And a bunch of molecules have a carbon backbone. In fact, carbon is so important that, like, literally in organic chemistry, if they want to show a carbon, they literally just draw lines. They don't even have to say that's actually a carbon because it's so important. And then just know what a hydrocarbon is. You literally could guess, okay? Why do I even need to tell you guys? Hydrocarbons? Hydrogen? Carbon? Yeah, basically it's stuff that's made up of hydrogens and carbon. Okay, now for the fun stuff, dudes. I love functional groups. They are my favorite. If you didn't notice I was sarcastic, it was, okay? So why don't we start easy and get progressively harder? So, the first thing we gotta talk about is hydroxyl. Hydroxyl, literally hydrogen, oxygen, hydroxyl. So, it makes sense. OH. Now we know from water, right? This OH stuff makes hydrogen bonds. Because oxygen hogs all the electrons, it gets a negative charge, and it makes hydrogen bonds. Very cool. Basically, these guys are called alcohols, but it's not very relevant. And the way you remember it is, look, there's an OH. Dang. So that's basically the important stuff you gotta know about hydroxyl. Then the next thing you gotta know is methyl. That's pretty easy to remember too, because you probably know that methane is CH4, right? But these functional groups, right, they're called functional groups because you could attach them to a molecule and they do a certain thing. You can't attach methane to anything. It already has 4 bonds on the carbon. So methyl, you just take out one of the hydrogens, and then the carbon now has 3 bonds and it's free to bond to something else. So see, like if you draw it like this, CH3. And then you can put whatever you want there. Epic. Now this guy is the only hydrophobic one. And basically the way you remember that is that all hydrocarbons are hydrophobic. And it's literally hydrogen and carbon. Epic. Then we got sulfhydryl, pretty self-explanatory. And this is basically SH. And the important thing about sulfhydryl is that they form disulfide bonds. Bridges, sorry. And you can probably remember that because there's sulfur and everything. There's sulfur in the name, there's sulfur in the bridges, there's sulfur in the formula. What else do you want? Now what's cool about the disulfide bridges is basically what makes your hair curly, if you have curly hair. And when you like straighten your hair, you're basically breaking the disulfide bridges. Alright? Another one that's pretty easy to remember is phosphate, because it's literally like phosphate phosphorus, right? Or you can think about it as a phosphate ion, which is like PO4. And it basically looks like this. You got your one O, you got another O, you got another O, and basically all these O's could bond to other things. Now this one's not that important, except the fact that it's like on your DNA or whatever. Okay, I think we filled one screen, let's fill another. I love functional groups so much. But dang it, dude, I gotta take off my jacket, it's so sad. It's too iconic. Okay, now we gotta talk about the carbo guy. So the first guy you gotta know is carbonyl. And basically, it looks like CO. And this guy's pretty boring. Basically, the only thing that Campbell talks about is that this is what defines a sugar. So basically, sugars are gonna have a carbonyl group. Then carboxyl. So carboxylic acids are a thing, right? So this gotta be an acid, but it also has carbo in it. So it gotta have a carbon, and then it also has like the same thing as carbonyl, except you gotta add something acidic to it, and you do an OH. So basically what happens is this H gets spit off, H plus, O minus, and see, it's acidic, right? It's giving off H plus ion. And the most important thing to know is acidic. And then the last one we gotta talk about are amino. Now, unfortunately, I don't have any good way to remember this one, but like, amine, anything that starts with like AMIN is going to be nitrogen based. So there's for sure nitrogen. Well, of course, you can remember using amino acids, and you know that amino acids have to have nitrogen in them. So basically, this is going to be amino group. You got a bond, so you could attach it to something, and then you know that N basically wants to form 3 bonds. So that basically means that you only have 2 more H's. Now the coolest thing about amino groups is that they're basic, and that makes sense, right? Because you know that NH3, which is ammonia, could become NH4+. So in the same way, this guy could snatch up a hydrogen, become H+, and hooray, you're basic, you snatched some hydrogens out of solution. Alright, epic functional groups done with. The only reason why you would have to know functional groups for the AP is like if they ask you like, given this structure of a molecule, what properties does it have? And you could basically say, it's an acid, or it makes hydrogen bonds if it has an OH, that kind of thing. Alright, now we had to talk about different types of bonds. James bonds, that's right. And basically the first type is ionic bond, and as you might expect, it basically means that the things become ionic, as in they're ions. Get it? Huh? Okay, anyway, so basically the most common like example of this is sodium and chlorine. So basically sodium has an extra valence electron, chlorine is missing 1 electron. So what happens is that sodium gives its electron to chlorine, so this guy becomes positive, this guy becomes negative, and now they're attracted. Hooray! Ionic bond. And the only thing you gotta know about ionic bonds is first off, they're pretty strong, and second off, they are between ions. So the positive guy is called a cation, because cats are positive, get it? Ha ha, okay, I'm done. And then the chlorines are anions, very cool. And, you got an N, negative, get it? Okay, cool. That pun was not even close to as bad. And then you got covalent, which basically means if you have like a C and an H, they share 2 electrons between them, and now they're connected. So 1 covalent bond is 2 shared electrons. If you had a double bond, there'd be 4 shared electrons. So each bond is a pair of electrons. And the 2 types are nonpolar, right? Because carbon and hydrogen have the same electronegativity, so they don't hog the electrons, very cool. Now OH is going to be polar because oxygen is a big, fat, greedy little piece of... what? Oxygen is just a bad boy, okay, it hogs all the electrons, and that's why it gets a negative charge. Alright, now we gotta talk about IMF. The 2 bonds we were talking about previously were between 2 of the same molecule. Now we're talking about between different molecules. Inter means between, molecular means molecules, forces means forces. Wow, that was some big brain stuff. So the first thing you gotta talk about, London dispersion forces. Basically the only thing you gotta know about this is just random, and because they're random, everything has it. It's just based on random movement of electrons. So all molecules. And basically a specific type of these are called van der Waals forces, right? So you've probably heard about gecko feet, right? They come so close to the wall that these random things, there's so many of these random things that it ends up holding them to the wall. It's really hard to like just put your hand and expect it to stick. I wish I could climb a wall just by using my hands, but the reason it doesn't work for us is because we have too many bumps on our hands. So like our hands are not that close to the wall, so the random interactions don't help that much. Okay, and then the other type of IMF is hydrogen bonding, which we've talked about so heckin' much, it's not even funny. But basically what they are is OH bonds, and they're so polar that they attract each other. And the reason why they're relevant is because they basically hold together every single molecule in the universe. Hold together biomolecules. I can spell molecules. Pretend that says molecules. Alright, now we gotta talk about macromolecules, and we are done. Let's do it. Macromolecules. Basically, these guys are big. One of the common misconceptions is that macro means like really big. It basically means that there are a lot of parts that come together. A lot of molecules come together. So basically, those things that come together are called monomers. Monomers, right? Mono, one, and then they come together to form what you think it is. Yeah, that's right, polymer. Because poly means multiple. So what type of biological macromolecules do we have? That's right, we got our carbohydrate molecule, and those basically are the CHO dudes. So like glucose is C6H12O6. That's going to be a carbohydrate. And there's basically three types, right? There's monosaccharides, which is like glucose. It's just one little hexagon looking boy. Then there's disaccharides, which are the two hexagon looking boys. And then you guessed it, there's the polysaccharides. Very cool. And because I'm getting tired of drawing hexagons, I'm not going to draw hexagons. But basically, these are just a bunch of the monosaccharides chained up in a very long thingamajigger. So there's a bunch of different types of polysaccharides. Basically, the things you gotta know is that there's glycogen and starch. And these guys are similar because they have the same type of bond. They're called alpha bonds. I wouldn't worry too much about what alpha bonds are. It basically means that they're all in the same orientation. None of the guys get flipped, but it's not really important. Basically just know that glycogen is very branched, starch is not as branched, but they both have the same type of bond. And then cellulose and chitin are different because they have beta bonds. Now the way I like to remember it is like glycogen and starch are for storing stuff, right? So they have to be easy to break down, and that's why they have alpha bonds. Cellulose and chitin are structural, right? Like cellulose is for your cell wall. You don't want that to break down easily. Chitin's for the exoskeleton of bugs. Why would you want that to break down easily? So they have a different type of bond called beta bonds that are harder to break down. Alright, epic. And then we got proteins. And basically these are just the guys that are made up of amino acids. And what the heck is an amino acid? Well, if you look at the thing, you got acid, you got amino. So what were the two functional groups that had acid and which one had amino? So there's amino, right? Amino is a thing. And that's NH2, right? And then we got a bunch of random carbon stuff here. And then what is acids? That's right, carboxyl groups. Because carboxylic acids are a thing. Just remember that that's a thing. So this is going to be COOH. And the only thing that's different between amino acids, there's 20 of them, right? The only thing that's different is this R group over here. This thing changes for different amino acids. Like glycine is like this, alanine is like CH3, and it keeps changing. And basically what happens is if you want to connect them, you basically take another one, pretend there's an amino acid there. And then basically what happens is, this is a very important fact, pay attention to this one, is in order to combine two monomers, you gotta do something called dehydration synthesis. Just wrap that really fast before your test so you know that it's dehydration synthesis. Because basically, if you know that, then you could say, how does this bond form? You gotta get rid of an H2O, right? So you get rid of one of these H's, and then you get rid of an OH here. So these guys come together, and beautiful, you got a bond between these two. So if you have dehydrated synthesis, how do you break it down instead? Instead of synthesizing, you gotta break it down. Instead of taking out a water molecule, you gotta put in a water molecule, and that's called hydrolysis. So I'll just write it here, dehydration synthesis versus hydrolysis. Hydrolysis is easy to remember, right? Because you're breaking it down, but dehydrated synthesis is not as easy to remember, but just remember that one is breaking down, so the other one gotta be synthesis. And basically proteins, the important thing to know about proteins is that they're used for every single important thing. Like enzymes are proteins, and enzymes literally catalyze everything in biology. So proteins are your toolbox, basically. Alright, we're almost there. 2 more to go. First, we gotta talk about lipids then. So the one thing you gotta know about lipids is that they're the most hydrophobic trolls in the universe. These guys are the guys who don't want to hang out with water at all. And the reason for that is because they're all basically hydrocarbons. So the general shape for a lipid is you got a glycerol molecule, and attached to it are a bunch of fatty acids over here. And the way you can remember this is it's literally called a triglyceride, right? So you got glycerol, and then you got 3 fatty acids hanging off of it. Now the most relevant of the lipids is phospholipid because it basically has a phosphate, call this a phosphate group, and then it has our glycerol molecule, and then it has all these 2 fatty acids instead of 3. So we know that this part is going to be hydrophilic, right? But then this part is hydrophobic. So this is very useful for a cell membrane, right? Because in a cell, right, you have water on the outside, right? And then you got cell stuff on the inside, which is also made up of an aqueous solution. So it's basically water as well. So you want a membrane that keeps stuff out, but you also don't want your membrane to hate water and just die when it's next to water. So the reason why this is cool is because your phospholipids line up like this. You got your phospholipid, epic, epic, epic. But if you just had one layer of phospholipids, right, on this side, but these guys hate the water. They literally want to kill the water. So this is not going to work. So basically what happens is that you make a double layer. And hooray, these guys are not next to water, they're happy. These guys are next to water, they're happy. Everybody's happy, so that's good. And as you might expect, this is called a phospholipid bilayer. Bio is very good at naming things descriptively. That's the one thing I can say about bio. Okay, just a couple more things to remember about lipids. Lipids also include like steroid hormones, and it includes like cholesterol and everything. And there's also a bunch of different types. So the first type is saturated, which basically means you have no double bonds. And that makes sense, right? Because if you have no double bonds, like, you can have as many hydrogens as you want. But unsaturated means that you have a double bond. So it's like that, you got a double bond. But carbon can only make 4 things, right? So if it has 3 things coming out of it, that means that it can only have 1 hydrogen. But if it only has 2 things coming into this 1 carbon over here, then it can have 2 hydrogens. That's why this is called unsaturated. Literally the only thing you gotta know is that it has a double bond. Just remember that. Unsaturated has a double bond. And then the last thing is trans fats. And you probably know, if you have any idea what you're eating, that trans fats are bad for you. And the reason for that is because they literally take unsaturated like fats that are from like plants and stuff, or fish, they have unsaturated fats, and they basically make it saturated. They put hydrogen into the thing. So that's why they're really bad. They artificially saturated. Saturated fats usually come from humans. No, we're not eating humans. Saturated fats usually come from animals and that kind of stuff. So that's why like butter or all the like really thick stuff that are solid at room temperature, those are saturated, right? And then fish oil and all the liquidy stuff like canola oil and all that are unsaturated. But then trans fat, you literally take the normal like unsaturated liquid stuff and you turn it into solid stuff. It's nasty. It's like shortening. I had no idea what shortening is until I searched it up. Search it up. It's kind of nasty, but people use it, but it's still like really bad for you. Alright, Epic, that's all we got to talk about lipids. Nucleic acid, now these guys are the most important guys to even be talking about. And basically the way that they're unique is that they have a phosphorus in them. So basically nucleic acids are called nucleic acids because they're a bunch of nucleotides, which are the parts that make them up, monomers. And they kind of look like this. You got your ribose sugar, you got a nitrogenous base, and you got a phosphate group. These are the 3 things you got to remember. Nitrogenous base, ribose sugar, phosphate group. That's all you gotta know. And it's pretty easy to remember if you think about DNA and RNA, right? DNA stands for deoxyribonucleic acid. So you got ribose, right? That's sugar, makes sense. The N for nitrogen. And then phosphate you're just gonna have to remember, but phosphate is really important, right? It's the defining characteristic of nucleic acids. It's the only polymer that we're talking about here that has a phosphate. And the reason why these guys are important is they carry genetic information and stuff. Okay. Well, actually, this should look a little bit more like this. Okay, the reason why I did that is because the carbon is here, and then there's the oxygen over here. Okay, so now let's talk about how the nucleotides come together, right? Basically how it works is you got your triangle here. Alright, it's not a triangle, pentagon, I know math. And then this is over here, and then you got a carbon, you got a phosphate, and then this one's attached to another one, which is like this, and then you start your pentagon again. And then this guy over here is attached to another phosphate from a different one, and then that's over here. Now the reason why this is relevant is that there's a right? There's a directionality to it, right? This flag over here is pointing up. This phosphate is up. So let's think about this a bit, right? So this carbon seems special, right? It's holding the nitrogenous base. So we start 1, 2, 3, 4, 5. This is a carbon right here. So we have 5 carbons, and this guy's a 5 carbon. This is 3 carbons. So the way we refer to the different sides of the DNA strand, this side over here is going to be your 5' end. This side is your 3' end. So if we went downwards, we're going in the 3' direction. If we go upwards, we're going in the 5' direction. The reason why this is relevant is that DNA can only be built in the 3' direction. Also, the 2 strands of DNA are opposite each other. They're called anti-parallel, and that basically means that one is this way, while the other is parallel, but it's going the opposite direction. Alright, epic. Also, these 2 things, they're parallel, right? Then you twist them around each other and you get a double helix. Like, something like that. I don't know how to draw double helixes. I'm not a double helix master, but that's how DNA looks. Very cool! Now, the last thing we got to talk about is how it relates to RNA. So, you got DNA, right? Now, the main difference is that DNA is double-stranded. It literally has a D in it, double-stranded. And RNA is typically single-stranded. Now, of course, you can have single-stranded DNA, you can have double-stranded RNA, but they're not as common. The other difference is the nitrogenous bases, right? DNA has A, T, C, G. You probably drill this into your head enough, because A pairs to T and C pairs to G. But then, for RNA, you got ALK. I don't know how to pronounce that, but you got AUCG. T got yeeted out of there. And the U stands for Europe. And basically, we just want to say what they stand for. A is adenine, T is thymine, C is cytosine, G is guanine, U is uracil. And then the one last thing you gotta know is purines versus pyrimidines. The way I like to remember it is pure as gold, right? So purines as gold, you got adenine and guanine. And the purines are hecka weird, dude. They got like a pentagon and then they got a nice little hexagon. The pyrimidines are a lot more sensical, and they're just like this. And these are the remaining ones, A, T, and C. Wait, what? No, U, T, and C. Very cool. Okay, I think we are done. Let's go. We made it through Unit 1. That was so long. What the heck? I thought Unit 1 was going to be a walk in the park, but apparently not. Alright, I hope it helped. Thank you guys so much for watching. If you enjoyed the video, leave a like, subscribe to the channel, do all that cool stuff. Let me know what other kind of videos you guys want. Don't worry, we're going to get out of AP mode soon enough. But until APs are over, we are on the grind, boys. Okay, that's enough. Thank you guys for watching. See you guys next time.